Okay, always remind me. Thank you. I'm keeping track of so many things here to get ready for class that I will inevitably forget something. So yes, thank you. All right. So what is constant? What does 60 miles per hour mean? It means for any variation in x, the corresponding change in distance is 60 times that change in x. So this is a full meaning, much better and complete than just every hour you go 60 miles, right? That's just saying dx can only be one. Every hour you go 60 miles is saying dx can only be one. We need dx to be anything, right? So and we'll see that later today, or we've been seeing that in what we've been doing. Okay, so the second principle was a net accumulation function we talked about. That gives the amount of variation in some quantity for any value of x when the rate of change is known. And then we talked about that realistic rates are often a changing rate. So rather than the flag lowering at a constant rate, if it's actually someone manually pulling the rope down hand over hand, then maybe this changing rate profile is more accurate than a constant rate the whole way. Okay, and then we came to this. So this is where we left off yesterday. And we had our accurate, the blue is the exact rate function. And we said, how are we going to move towards accumulation? Well, to move towards accumulation, we need to use dy equals m dx. But we can't use that if our rate is changing. So we said, okay, let's make a pretend rate function. Let's make a new rate function that's trying to be like the exact rate, but that's made up of constant rates. And then we can use dy equals m dx to calculate changes in height, right? And so the way that we did this was we estimated like an average rate in every interval. We eyeballed it. We said, oh, look, it's kind of like all the rates from negative 0.5 to 0 and back to negative 0.75. And so as an average, as something in the middle, I said negative 0.4. And you might say negative 0.5, or you might say negative 0.45. So this was like an eyeball estimating the average rate in each interval to be the constant rate in that interval, okay? So like for this one, it's like, oh, we see all the rates from 0 to negative 0.75, but then there's a big chunk of this interval that's all at negative 0.75, so that's gonna kind of bring the average down. So we estimated the constant rate in that interval to be around negative 0.6, kind of below halfway. So we did that for every interval, and we built this pretend rate function that has constant rates. Why? So that we can, with those constant rates, we could calculate changes in height. We calculate, and this is moving towards accumulation of height, right? So we had built this table. And for this table, so again, for questions, you can interject verbally whenever you hear a break. You're free to speak out, and then also you can ask a question in chat, and one of our TAs will be monitoring the chat and answering questions there. Just don't get into too long of a conversation so that you get behind.
I have a real quick question.
Sure thing.
So the x-axis was time elapsed in seconds, and then the y-axis was showing us the rate.
This is the rate graph, right? So this is the rate of change. The exact rate is the blue one.
Okay,
and then the approximate rate, we're building a pretend or approximate rate function is the red one.
So and like we get the y-axis were the constant rates, like that's how you got those numbers, right?
Right. So like the average here, so like I'm saying somewhere between 0 and negative 0.75, somewhere in the middle is about negative 0.4. That's that y value right there for the rate of change. Does that answer it?
Yeah. Sorry, I just forgot what the y-axis was.
Yep, this is the rate of change graph. So the y values are in meters per second. Okay, so, and then we built this table. And we built this table based on our new pretend rate function to try to move towards accumulation or tracking changes in height, right? Get from the rate of change. So where do we see how fast the flag height is changing at every moment? So what columns give us a function for how fast the height is changing at every moment? So that would be these two columns, right? Given any time elapsed, this was our approximate rate of change. This is the red rate function, the approximate rate function. And so the reason that this is staggered is because these rates are in intervals, right? So this rate is from 1.3 to 1.65. It's the constant rate of negative 0.75 that we estimated. And so then you see, so that rate applies for all x values from 1.3 to 1.65. So the first two columns are how fast the flag is changing every moment, right? And that came from our exact rate function. And then where in the table do we have how much accumulated change in flag height is there at every moment? So which table or which column or columns in the table would give us that function? Right, so the question is, you know how fast the quantity changes every moment? That's this function. You want to know how much you have at every moment, how much has accumulated at every moment. Okay, so where's that in the table? Well, that would be, again, time and this column. What did this column give us?
Net accumulation.
Right, so it'd be how much the height has gone down since when? Since 0.6. Okay, so these values were our MDXs. It was the approximate change in height in each individual interval. But then what are we doing? It's accumulation, right? So accumulation comes in this column where we're having a running total of those changes. So it always gives us how much change since 0.6. So like this number right here, what is that? Negative 1.435. That's at 3.05 seconds since we started lowering the flag. We've accumulated this much change in height since 0.6 seconds, right? It's the accumulation of all these changes up till 3.05 seconds. So this is the total variation in height since our 0.6 reference time. Okay, does it make sense? So individual changes in each interval, then this is the accumulation of those changes. So it's the total variation since our reference point of 0.6 seconds. Okay, so that's review. Any questions on that?
I have a quick question. So for question 1, when we're talking about the columns, the approximate rate of change, that would be where question 1 is, right?
Yeah, the first two columns forms the red function, the approximate rate function. Because
Okay.
this column here is the value of these approximate rates.
Mm-hmm. Okay, and then question 2 is like that third column, right?
No, the first and the fourth.
Oh, okay.
Accumulated change in flag height, right? That's the fourth column. These are individual changes in each separate delta x interval.
Okay, that makes more sense.
This is the accumulation of those changes. So it's the total variation since the beginning or since 0.6. So if we want accumulated change in flag height, that's this one here. Okay.
Okay.
So let me... Okay, so moving on here. So we're going to keep talking about the pretend rate function. So what was the first method we used for the pretend rate function? Back here. What did we do? We eyeballed. We estimated kind of the average rate, or like the best one rate that could model what's happening with the changing rate in each interval, right? So we're eyeballing like that kind of an average rate of change in each interval. That was the first method to build this approximate rate function. Okay, so now we're gonna do a second way of approximating the pretend rate function, and this is called the left-hand method. Okay, so this is a new way of creating that red approximate rate function, and this is a little more systematic. And by doing it this way, if we did it separately, we'd all get the same thing. right? So we said before this estimating method, we would all kind of have slightly different values for what we think is the best guess at the average rate in each interval. Okay. Now this method, the left-hand approach, is going to be more systematic, and it's going to be the same for everyone. Am I still sharing my screen?
Yes.
You can see. Okay. All right. So what we want to do is, rather than estimate like an average rate of change in each interval, we're gonna use the actual rate from the blue graph. We're gonna use the exact rate of change at the left-hand side of the interval, or the beginning of the interval, and then just let that be the constant rate for the whole interval. Okay, so for instance, this first interval, starting at 0.6, what is the actual rate of change at the beginning of the interval, or at the left-hand side of the interval?
Negative 0.75.
Yeah, so here's the interval starting at 0.6. So when we look at the graph, right there, that point is at about negative 0.75, right? So it's negative 0.75 is the actual rate at the beginning of the interval. So for this interval, we're going to let the constant rate be that value. So I'm going to grab this here and put it right there. I think. Okay. So for our first interval, we are estimating at the left hand. Yeah. So we said for interval number 1, the left hand is going to be negative 0.75 meters per second. Okay, and so then I let that be the constant rate for the whole interval. Okay, how about the next interval? So looking at the next interval from, what is this, 1.95 to 1.3, what is the actual rate at the left side of that interval? So looking at the graph, looking at the left side or the beginning of the interval, again, so looking at the graph here, it's here. It's again at negative 0.75. So I'm going to let that be the constant rate for the whole interval. So for interval number 2, again, negative 0.75 meters per second.
I have a quick question.
Yeah, sure.
So how big are these intervals? Oh,
These are the same as before. So this is the delta x is the 0.35.
Okay, that's the only question I had, because we'll know.
Yeah,
like,
sorry. So that was
we
we're doing the same intervals as before. Yeah.
Okay, thank you.
So this is 0.6, 1.95, 1.3, 1.65. What would that be? 2.0, 2.35, 2.7, and 3.05. Okay, next interval. So what do you think, what is the exact rate at the left side or the beginning of this interval? Is it negative 0.75 again?
Oh.
Is it
I don't
negative 0.7?
Negative.
Yeah,
Zero
like around
point-
negative 0.7. So I'll move it down here, and then maybe after I get it there. How'd I do? Pretty good?
Perfect.
So what would we say? Negative 0.7 or negative 0.65 or something like that? I can move, actually, I can just, you can use. Negative 0.65. Do you see that?
Yeah.
I have a question.
Please.
Could you repeat how you reached the change for the exact rate function for that interval specifically?
We're looking at the exact rate function, which is the blue graph.
Uh-huh.
And we're looking at that rate at the left side or the beginning of this interval. So for this interval, we look at 1.3. What is the actual rate at 1.3?
I see. So we're not taking into account any of the values in the
Nope.
interval because we're using a left-hand
Yes,
method.
good point. We're just taking the exact rate at the beginning of the interval. That's the only rate we look at, and then we let that be the rate for the whole interval. Does that make sense?
Yep.
Okay. All right, next one. So we'll go a little faster now if we're getting the hang of it. So the next one is going to be, if you look at the rate at the left side, negative 0.75 again. Boom. All right, what about the next interval? What's about the rate at the left side of this next interval starting at 2, x equals 2?
Negative 0.2.
Yeah, so maybe right there. How'd I do? Oh, too low. Maybe something like right there. And that is right. So I think negative 0.2 is a good estimate for that. Everyone see where I got that? So for the fourth interval, constant rate, negative 0.2. All right, fifth interval. From 2.35 to 2.7. Again, here's the actual rate, negative 0.75. Sixth interval. What about there? Let's see here. So I'll move this one down. This one. I think it looks like right about there. So I think negative 0.2 again. Is everyone tracking with me? And then the last one, again, negative 0.75. So again, what are we doing? We're pulling off the exact rate at the beginning or the left side of every interval. That's why it's called the left-hand method. And then we ignore the rest of the interval. And we let the constant rate just be that value of the exact rate at the left side of the interval. I've got one more to move here. So now here's what the pretend rate function looks like using the left-hand method. Okay, so what do you think will give us a better estimate of accumulation? When we eyeballed and did the average, or this one?
The average.
Yeah, because we did our best to try to pick one rate that was like the average or replicated the rate in that interval as best we could. These don't do that. All these do is just pull off the rate at the beginning of every interval. So like for this one, this is a very bad approximation for this interval, right? See this? Because we estimated it to be down here, like below the halfway point, which is a much better average, a much better estimate. But using the left-hand method, you get this very bad approximate rate in that interval. See that? Right. Okay. So yeah, I would guess also that our estimate approach would be better. But the advantage to this is that there's no fudging. Like we all get the same thing when we do this. Okay, so we had to estimate these values by looking at the y-axis. All right, but this is an exact science. There is exact rate values at the beginning of every interval. How could we express those? How could I express this value exactly if it's not exactly negative 0.75? How can I express exactly what it is?
R of 0.6.
Good, right. So actually R sub h, right? So that first rate expressed exactly is, this is what we're working on, function notation. R sub h of what value?
0.6.
0.6. Does everybody see that? This is super important. So that's exactly what the R function is, the approximate rate in the first interval. Okay, what about in the second? R sub h of 1.95, or the exact rate at the beginning of the interval, the left-hand side of the interval, etc.
Would that be 1.95 or 0.95?
0.9, yeah, thank you. Okay, and so this is what we did. Create an approximate rate function that uses the rate values you estimated and expressed above to form the constant rates in each interval. That's what we did at the beginning. So all these rates taken together, form our R function. The approximate rate function based on the left-hand method, or the exact rates at the beginning of every interval. So this is what's called a piecewise function, R sub x. Usually we write it vertically. R sub h of 0.6 over the interval from 0.6 to 0.95. R sub h of, actually we need it to be closed here, 0.95 from 0.95 to 1.3, etc. So this is the interval of x. And then this is the function value. And so we could keep doing that. And this is called a piecewise function, right? Because our approximate rate function is broken up into pieces. It's all these constant rates over different intervals. And so that forms this approximate rate function based on the left-hand approach. Anybody have a question on that?
Yeah, I was just wondering, so is it a closed bracket for starting at R sub h of 0.95 and then a closed bracket for 1.3? Or
it should be closed here.
So that should be closed and then the left side should be open?
This is a different conversation.
Okay.
So, yeah, so intuitively you would think that it should be closed on the left, but there's something going on here where it needs to be closed on the right. But for our purposes now, it can be closed on the left. That's fine.
Okay, thanks.
This is a different can of worms that I don't really want to get into right now. So don't worry about what's closed and open. Just the idea here is that for each interval between two x values, you have this constant rate that you're picking off from the exact rate at the left side of the interval. Okay, other questions?
So just to clarify,
yeah.
The rate of change x, which is like the approximation, when we're doing the left-handed method, we figure that out by how many intervals we decide to put in whatever, I guess like how many intervals we put in a certain space. I don't know how to explain it quite right.
Well, we could have shows, we're just building kind of this part of it, right? It keeps going. But I just have showing this much of the exact rate graph. So we just stopped here, but the height, the flag is still descending. And so we would keep going.
Yeah, okay.
So the number of intervals is not really a really crucial point here. The width of the intervals is important. But we're just doing a sampling. We're starting off building this approximate rate function, and it would keep going until the flag reached the ground or the soldier's hands or whatever. Is that okay?
Yeah, that makes sense.
All right.
Good question.
Yeah, please.
Is this to help us understand it conceptually, or is this a method we'll be tested on?
Yes, both. So we're always going to emphasize the concepts, and then you're going to be tested on the concepts.
Okay.
Yeah. Okay. So let's move on to the next thing. So I'm going to show you this kind of in a dynamic way. We said what principle 0 was variables vary, right? Variables vary. So I have here's can you see the exact rate function here?
Yes.
And here's this left-hand rate function now being generated. We're thinking about, okay, there was a point in time where the flag was being lowered, and X was taking on all these values of time in seconds since we started lowering the flag. And so then, as that was happening, this information was being generated, and so this is the rate of change occurring kind of in real time, right? So, and then I'm showing the approximate rate function that we just built as if it were the actual rate function as time goes by. So variables vary, right? There was a point in time when this flag was being lowered, and our approximate rate function was being generated point by point. Okay, so is this accurate to what we came up with here? Yeah, so we had these two as the same. We're eyeballing it, but it looks like this next one's a little bit lower. Okay, so what we want to do now is we want to think again about, now we've got this approximate rate function, we want to build accumulation, or accumulation in the changes of height. Accumulation in the changes of height. So remember, where will that? So this is at 0.6 seconds. So for accumulation function, what will our net accumulation be at 0.6 seconds? So here I'm at 0.6 seconds. What will my net accumulation since 0.6 seconds be?
0.
0, right? So there's been no change since 0.6 seconds. And then what will happen? The flag will start lowering at a height of negative 0.75 meters per second. That's our approximation. We'll do this together. So for that first interval, the flag will start lowering at negative 0.75 meters per second. And so that's what that graph will look like, accumulating changes in height at this constant rate. The next interval we said had the same constant rate based on the left side. So the change in height will continue to be more negative through that interval. So this now is the approximate accumulation function based on our approximate rate function. So what's going to happen in the next interval? So in the next interval we said, I think it was around negative 0.65 was the new rate. So what's going to happen with this accumulation, this approximate accumulation function? What do you expect to see when I take us through the next interval?
It's going to go at less of a negative slope.
Good, right. So it'll have a less negative slope. It'll be a shallower decrease for that next interval. Just slightly shallower. Can you see how it just kinked a little bit? And then it's going to go what? Back to the original slope of decrease. And what about the next interval?
It's going to be a lot more shallow.
Yeah, a lot more shallow. Now this was we said negative 0.2, and it's maybe closer to negative 0.1. So according to the left-hand approximate rate, we're going to have this constant rate for the whole way, which is a very slight decrease in height. And then back to the steepest, negative 0.75. Then back to a shallow decrease, etc. And then steep again. So here's the net accumulation function, the approximate, based on our approximate rate function, which was using intervals of 0.35 and based on the left-hand approach, right? The left-hand approach.
I have a question.
Please.
So just to be clear, on the left, the graph is the approximate rate function, and on the right, it's the net accumulation?
Yeah, right.
Okay, awesome. Thank you.
And then more than just labeling it, we're really talking about, like, when you look at that, it should be like, oh, of course, that makes sense, right? Because our rate of change, we're approximating with constant rates, so that we can use dy equals mdx, right? And so then what? The flag is accumulating a decrease in height through here. So that's what it's doing. It's showing these y values here show how much decrease we have since 0.6. And then the rate of decrease will change according to our approximate rate function. So when that was a low rate of decrease, we see less changes through those intervals. A lesser contribution to the decrease in height in those intervals where the rate of change is a lower negative value. Okay, so let's look at how would we calculate. So we want to come up with, in terms of how much do we have at every moment, we want a function, right? We did that in table form, and we talked about that yesterday and today at the beginning of class. Then in table form, we came up with kind of a representation of that function as distinct points, but we want a continuous function. We don't want just distinct points that you get from a table. We want a continuous function for the approximate accumulation. So we're going to call it a of x. And so to kind of figure out what the structure of that approximate, the continuous function is, let's take a particular example and let's look at 2.15. So where's 2.15? Right here. So I want to look at 2.15 and let's build what the value of a of 2.15 would be. So come down here like this. Please stay straight. Pretty good. Okay, so what am I after here? I'm after what is the net accumulation in the height of the flag since 0.6 seconds when we've reached x equals 2.15 seconds. So let's build. So what would that take? What would it take to build a of 2.15? What is that going to look like to calculate that total accumulated net change in height since 0.6 seconds? What would that look like? How would we get that? Anybody?
Are we finding like the area under the axis, or are we just going to look at the y-axis?
We want to use what we've been learning, right? Let's use what we've been learning. Haven't talked about area yet.
Wouldn't it be the y value of the graph on the right at 2.15 seconds?
Yes, exactly. And I want to calculate that. I want to get a computation for that so we can build a function for that. Exactly, yeah. So it's this much change in height, something like something here. So how do I get that?
Would you start by adding up the left hand rates up until then?
Are we going to add the rates? Am I going to add the rates together? What am I going to add together?
Oh, I'm sorry.
Rate times the interval.
Right. So this, remember how we built the table, accumulation is, it's going to be, we're going to add up changes from each interval. And how do we get the change in each interval? dy is?
Rate of change times dx.
mdx. So I'm accumulating up all the change to this point, which is going to be the accumulated change in that interval, plus this, plus this, plus this, and then we got something different going on here. So we're going to have what? We're going to have our r, using our approximate rate function, we're going to have r of 0.6 times how much change?
Negative 0.75.
No, how much change? So that is the negative 0.75.
0.35.
0.35. Okay, notice how it's important that we need the full meaning of rate of change, right? I'm not doing a change of 1. Remember, for any change in x, the change in this case, height, is that change times the rate. I need that full definition. Only knowing how much change we get for a change of 1 unit is not going to be good, right? I need to be able to know how much change I get for any change in time. M dx. Continuing. So then I want the change from the next interval. Times? Is it going to be 0.7 now?
0.35.
0.35 again, right? It's this rate now for its duration, 0.35. And then I'm using my approximate rate function at is that 1.2 times dx. In this case, in this delta x, plus r of 1 point, did I get this right? 2. Oh, that's
1 point.
Did I miss one? 0.6, 0.95.
You did 1.2. It should be 1.3.
1.3, and then 1.65. Is that right?
Yep.
Yes.
Thank you. Now, how much change do I get? This is what we call the current interval, right? It's where the current value of x is. We have these completed intervals, and then we have the current interval. So what's the rate in the current interval? It's still r of 2, thank you, times 0.35?
Yeah.
No, it's
gonna be, I think it's gonna be like 2.15 minus 0.35 or something.
It would be
How much change do we have? How much change in the current interval do we have so far?
0.3.
0.15 amount of change, right? All these changes are 0.35, but now we're only partially through the current interval. How far? From 2 to 2.15 gives me a dx of 0.15. Remember we said dx is a variable. Remember we said that? Dx is a variable too. It's varying in the current interval. So these delta x's are fixed, 0.35. But in the current interval, dx is increasing. Right now, when x is 2.15, the current value of dx is 0.15. It varies from 0 to 0.35 in this interval. And if we pause at 2.15, then dx is 0.15. So the structure of this is, it's going to be total variation from completed intervals. Right? That was adding up these first four m dx's plus a little more variation from current interval. That's going to be the structure of it. The approximate accumulation function. It's that we're going to sum up all the total variation from completed intervals, and we're going to use summation for that. Plus a little more accumulation from the current interval. So it's going to be the sum of a bunch of rates, the left-hand rates, times delta x, plus the rate in the current interval, CUR, times dx, just that partial interval width. Okay, remember you got the homework, based on the recitation. It's due Friday morning. Don't forget that homework, and then also be looking for new homework coming up Wednesday. Your quiz is open. Go take your quiz. I'll stick here in the room for any questions.